are going to be a bit more specific than the last couple. So the fourth one is all about kinetics. So reaction rates, both from the big picture point of view, looking at what sort of factors can affect the rate, and also from a more detailed point of view, thinking about what's happening to the actual molecules during reactions and during collisions. So the concepts under this idea, first we're going to talk about factors that will affect the rate of a reaction, and then how to use our stoichiometry relationships in reaction rates, how to write a rate law, and also use the rate law and the integrated rate law and graphs in various calculations. We'll look at energy distributions, potential energies, collision mechanisms, and catalysts. So first up, we talked about 4 factors that affected reaction rates. The first one was the physical state of the reactants, their size, their homogeneity, their surface area, things like that. Because if we think about a reaction from the kinetic molecular theory, in order for a reaction to occur, 2 atoms have to physically come into contact. They have to hit each other, they have to interact. And so anything you can do to make those collisions more likely will speed up the reaction. So if you have a more homogeneous mixture, reactant atoms are going to find each other sooner. They're going to start closer together, and so the reaction rate will be faster. The next factor is temperature. Again, thinking back to kinetic molecular theory, we know that as we increase temperature, we increase the kinetic energy and the speed of our particles, and so there's a twofold effect here. First of all, the particles are moving around a lot faster, and so there will statistically be more collisions because those particles are moving faster. They're going to collide more often. But the collisions that do occur will also be more effective because the particles are moving faster. They're moving with more kinetic energy, and so the collisions are going to occur at higher energies as well. The third factor is the concentration of the reactants. Again, we need collisions to happen for a reaction to happen. So the higher our concentration is, the more collisions there's going to be. If we cram more particles into the same space, they're going to run into each other more often. It's going to be harder for them to avoid each other. And finally, we know that we can add a catalyst to a reaction to increase the rate, and this works by decreasing the activation energy. The catalyst provides a new mechanism, a new pathway for the reaction that is lower in energy. There's less of a barrier to be overcome, and so the reaction is able to occur at a faster rate. Here's an example of what a reaction rate plot might look like. There's a couple important things to note in this graph. We've got concentration plotted against time. So here's our initial rate. Right when we begin, we have a high concentration. The slope of this line here is fairly steep, indicating that our rate is fairly fast, and then the slope starts to decrease as we go. We're using up reactant. There's less and less concentration of our reactant, so there's going to be fewer collisions, and our rate's going to slow down as we start to use up our reactant and our reaction proceeds. So we always use the instantaneous rate when we're talking about the reaction rate typically. So remember that if you just want an average reaction rate, you could pick any 2 points on this line and take the change in concentration over the change in time, and that would give you an average rate between those 2 time points. However, if you're not looking for a window of time, if you want the rate at just one specific point in time, then you're looking for the rate, the slope of the line, at 1 point. And so to find that, you draw a tangent line to that point. Here, at 600 seconds, to calculate the instantaneous rate at just this one point in time, we've got this line here. It's tangent to the curve. It only touches the curve at 600 seconds. And now we can find the slope of this line just with delta y over delta x, rise over run. Same thing here. We had a tangent line that's tangent at the instantaneous point at time t equals 0, and we could find the slope of that line to give us the instantaneous rate. Remember that reaction rates or rate laws can't be written just from the reaction coefficients. We do have this general relationship that for any reaction, the rate would be 1 over its coefficient times the change in that in the concentration of that species over the change in time. There's a negative sign for both of the reactants. No negative sign needed for the products. All of these are equivalent ways of expressing the rate. 1 over the coefficient times the change in that compound or element over a change in time. And the reason these are equal is because as we could decipher from this equation, if A disappears at a certain rate, B must also be disappearing at a rate relative to that. C and D must be appearing at a rate that's related to the disappearance of A, and they're all related by their coefficients. So if A, for example, let's, for the sake of this argument, just assume all the coefficients are 1. If A is being used up at 2 moles per second, A is reacting with B. B also must be being used up at 2 moles per second. C and D must be being produced at 2 moles per second. If the coefficients over here are 1 and the coefficients over here are 2, then A and B could be being used up at 2 moles per second. C and D are being produced at 4 moles per second. Here's another way of expressing concentration and rate. You could be given a data table with various experiments, and we've got different initial concentrations of our two reactants. And as we vary these initial concentrations, we are measuring the initial rate. And you can use a data table like this to write your rate law. So remember, the general form for writing a rate law is going to be rate equals K, the rate constant, times the concentration of each of our reactants. Remember to put concentration in square brackets. And then you would go and you would look at the data table for each of your reactants. So you start with NH4. Looking at experiments 1 and 2, we see that the initial concentration of NH4 doubles here, while the initial concentration of our other reactant doesn't change. Meanwhile, the initial rate is also doubling. So we've got a proportional relationship there. If the concentration of NH4 doubles, the rate doubles. So there would be an exponent of 1 on the NH4 in our rate law. The reaction is first order with respect to NH4. And you could do the same thing for NO2. And then here would be your finished rate law. So you could say that the rate is first order with respect to NH4, first order with respect to NO2, and the overall reaction order is just the sum of all the exponents. So this reaction would be second order overall. Here's a reminder of the relationship between first, second, and third orders and their rates. A zero order will be a zero order reactant will be independent. It won't change or influence the rate. So a reaction that is zero order with respect to one of the reactants means that the initial concentration of that reactant has no effect on the rate. First order, if we double the reactant concentration, we double the rate. Second order, if we double the reactant concentration, we quadruple the rate, 2 squared. Third order, if we double the reactant concentration, the rate would increase by a factor of 8, 2 cubed. And then you can go back and you can calculate K, the rate constant, for your rate law. Let me go back a slide or two. Once we had this rate law here, we could pick any one of these lines and plug in the initial concentrations and the rate to solve for K. Just be careful when you do that to actually include your units and solve for your units, because the units on K will change depending on your rate law. Here's a quick reminder that you can determine the order of a process by looking at its graph. So for a first order process, we see that as the concentration or pressure decreases as time moves forward and we use up our reactant. And we could plot this, the linear plot for this is the natural log of the pressure or concentration. So if you see a linear plot and it's plotting the natural log of pressure or concentration, that indicates to you that the reaction is first order, and you can find the constant from the slope of that line. Second order is very similar. So for our earlier, no, this is a different example. Second order is similar, but instead of graphing the natural log of the concentration, graphing 1 over the concentration is what gives us a linear plot. So if we've got a series of plots and the linear one is 1 over the concentration, that would indicate to us that this is a second order process. Here's a summary of those relationships for 0, first, and second order. We know what our rate laws look like. This is just a reminder of what the integrated rate equation looks like. In case you need to use those, you might keep this table in front of you as well. And then, more importantly, I think a reminder of what is plotted to get a straight line for each of these. So if you've got a series of plots and only one of them is linear, you just look at what is on the y-axis of that plot. And whatever is on the y-axis should correspond to one of these. The slope will give you the rate constant, and then I included what the units on that rate constant would be. You fortunately don't actually have to do the memorizing because you get to have whatever notes in front of you want. So I might include this table. Another reminder, remember that the half-life, by definition, is the time it takes for half of your concentration to be used up. So I believe in our notes earlier, we've got this table, and there's another column for the half-life equations. And now you can derive all of these because you know that at T1 half, at the half-life time, your R initial is R initial, and your R at time T is 1/2 R initial. So you can solve for the half-life using the integrated rate equation by just plugging in 1/2 R initial for RT anywhere. But we do have it elsewhere in our notes as well, a table of the various equations. So for first order, we have the expression that K is equal to 0.693 over T1 half, or in other terms, the half-life is equal to 0.693 over K. And this was important because it indicates that for first-order reactions, the half-life is independent of the initial concentration. it doesn't matter how much you start with. It's going to take the same amount of time for half of it to be used up. If you start with 100 moles per liter of your reactant in a first order equation, and it takes, let's say, 5 seconds for you to be down to 50 moles per liter, so it took 5 seconds for half of your concentration to be used up. It would also take that same 5 seconds if you started at 1,000 moles per liter and waited for 500 moles per liter to be used up. The initial amount doesn't matter. It takes the same amount of time. We can use reaction coordinate diagrams to help us visualize the energy changes that occur during a chemical reaction. So we've got potential energy plotted here and our reaction pathway or reaction completion. This is just a reminder. The change that we have between our reactants and our products, that's our delta E, our energy change for the reaction. The change between the reactants and the peak is the activation energy that needs to be overcome. And then remember that catalysts work by decreasing the activation energy. They provide a different pathway for the reaction. The start and end points do not change. We're still reaching the same products at the same energy. We're starting with the same reactants at the same energy. We're just taking a different route to get there. And it happens to be a faster, lower energy route. Here's one more reminder. We've seen this graph a couple times now. It's demonstrating that as we increase temperature or as we increase kinetic energy, our curve here, plotting how many molecules have each value of energy, spreads out. So at low temperatures, we don't have very much variance in our kinetic energy. The average kinetic energy is right here. It's fairly low, but there's not a lot of variety. It's a greater fraction of molecules are close to that average value. As we increase the temperature, our average energy, our peak, shifts over, so now the average particle is at a higher energy, and our curve is also getting broader, so now there's a greater variance in energy. If there's some threshold kinetic energy where say the activation energy that needs to be overcome for a reaction, increasing the temperature shifts the curve over, broadens it, and means that a greater fraction of our particles have that required activation energy. All right, last idea. Remember we talked about reaction mechanisms, which were ways to break a reaction down into single steps, step-by-step processes. And so if you break your reaction down into those steps, you could do a couple things. You could find the rate determining step, which would have been the slowest step in your mechanism. And when you are working with just a single mechanism, you are able to write your rate law based off of the coefficients. Finally, there were these vocab words for describing the molecularity of a process, and all that does is tell you how many molecules are involved in the process. So here, there's one molecule involved in this elementary reaction. It's unimolecular. In a bimolecular reaction, there are two pieces involved, two reactants, and the rate here could be written as A squared, or it doesn't have to be the same reactant. We could still be bimolecular and have two different reactants, and the rate would be written as the concentration of A times the concentration of B. It doesn't matter. Both of these still have two molecules reacting.